Hello everyone, this is Dr. Sharif and today we are going to have a video of drawing shear and moment of frame. If you can remember this frame, we already solved it together and we got these reactions in a previous video, so you can see the video to see how we calculated these reactions. Within this video, we'll be concentrating on drawing shear, force diagram and bending moment diagram. Okay, for the shear force diagram, as I told you earlier, we start from the left side and we follow the sign convention of shear. And if you want to remember, the sign convention of shear is like that. If you are going from left side going up, this will be, or from the left side, right side going down, or left side going up, this will be like a positive shear. And if you have the opposite, it will be a negative shear. So it would be very easy for the shear to start from the left side, and if you are going upward, it will be a positive, and if you are going downward, it will be like a negative. Okay, how about frames? In beams it is easy, but for frames, okay, you have different parts of the frame. You have a column, you have a beam, you have another column. So where to stand, where is your left and your right? Okay, to do that, okay, let's say if we are dealing with this member AD, so you stand like that. You assume yourself you are like here, and then therefore your left hand will be like that. And if the load is going up, this will be positive. If it is going down, it will be just negative. And we are going to repeat the same for the beam. You just change your position like that, and this is your left hand. And if you are going up, it will be positive. If you are going down, it will be negative. And the same for the last one. You come and assume yourself you are here. Okay. And then this is your left hand. And if you are going up, it will be positive. Going down, it will be negative. So let's start doing that for the first part of the frame, which is member AD. This member AD. Okay. So if you are sitting here, this is your left hand, and then if this is going up, this will be a positive. So we can find that we have 24 kilonewton going up compared to U. So this will be like a positive 24. This is going to the left direction like that. So you will come at this point and then you will go 24 going up. So this is a 24 going up like that, and then we can write here 24, and this will be a positive shear. Then we have this 24, and then we have linear, or like we have a constant or uniform load here. So uniform load, it will give you a linear shear. So how much you will go down? You will go with a value of 48, but linear. So 24 positive minus 48, it will be minus 24. So you will have a value here of minus 24 somewhere here, and then this will be like a linear going down like that until this value, which is minus 24, and therefore outside here is positive, inside will be like a negative. This will be our first shear. Then you reach it minus 24, you should go back again to 0. What will take you again to 0? If you just look here, what are the horizontal forces coming here? You will find only this 24 will take you up again to 0. So you will close the shear at this point like that. So you go up 24, then linear minus 48, and then up 24 again, which is this one that will close it directly to this point. And this will be the shear for the first element. Now let's move to our second part of the frame, which is the part DC. DC is like a beam. So you assume yourself you are like that, and this is your left hand. And if you are going up, it is positive. So to do that, just look at this point for all forces perpendicular to the member DC at point D. You will find that you will have only this force, which is 30.8. 24 and 48 are horizontal, so they are not making any shear on member DC. The only force, it will be 30.8, and it is going upward. So what we will do here, we will come from this point and we will go up with a value of 38 or 30.8. This is the value. Then what to do? You will find that you went up here 30.8, but you have this is going down 100 down. So this will result in 30.8 minus 100. How much it will give us? It will give us 69.2. So you will go down from here to reach a value here, which is 69.2. So this is 69.2. So what else? You will find that this 69.2 will take you again up to 0, because at this point, what is the force here? 69.2 will take you up to 0 again. So it will be going to 0 here. So we started from 0, going up 30.8, which is this one. Then we went down linear with 100. Then we went up again 69.2, which is this value here, and we resulted with this shear, and this will be like a positive, and this will be like a negative shear. So what else is still remaining? We still have this member CB. For member CB, okay, what to do? We will come and we assume yourself you are sitting here, and this is your left hand. If you want to start from the left, if you are going up, it will be positive. So to do that, just imagine here how much it will be the forces perpendicular on member CB here. So what will be the force here from all of these forces? It will be the horizontal forces. So what you can find here, you will find like 24 going to the left, 48 going to the right. So the resultant of that, it will be like as a 24 kilonewton, which is the resultant of 48 and 24. So from this point, I will go outside positive, because from left hand going up, it is positive with a value 24. So let's do that. We will come to this point, and then we will go up with a value 24. What else? Nothing is here, no more loads here. So you will go parallel to your member. Let's just move this one a little bit away. Okay. Then for that member here, you have a 24, but nothing here. So you will go parallel to your member until you find that 24 that will take you again to 0. So we will have here parallel to the vertical member, and then we have a 24 that will take us to 0 again. And any shear which is outside the frame will be positive, inside will be negative. So this is the shear force diagram. Okay, now let's move and draw the bending moment diagram, but keep in mind that if the shear is linear, the moment will be curve. If the shear is linear, so the moment will be curve. And we know that at the 0 shear, we have a maximum bending moment. At the 0 shear, we have maximum bending moment. So let's move to the next page and draw the bending moment diagram. Here, I'm trying to teach you how to draw the moment even without shear, because I know like many students, they have to draw the shear first to be able to draw the moment. And if you have a mistake in shear, you will have the same mistake in moment. So let's draw the moment without shear. As I told you, like there are important points. Once you have them, you will be able to draw the moment. So at the beginning here, at this intersections, okay, or under any concentrated load. So in our case here, we have only this point, and at this intersection, and at this intersection as well. 4 points. Out of these 4 points, we can see that 2 of them are zeros, because this is an end pen or ruler support. So the moment here will be 0. So we can put it as a 0 here. It will not change. And again, at the second pen or ruler support, the moment will be 0. So this also will be 0. We also have an intermediate hinge at this point. There is an intermediate hinge. So for intermediate hinge also, we know the moment will be 0. So therefore, this also will be 0. So out of the 4 points, we have 3 of them are zeros, okay? So the only missing point will be this point at point C. We can get the moment here by taking a section at this point, and you can take a moment from the bottom side, or you can take the moment from the left side here. I think this one is much easier, so you can take it from the easier side. How to do that? You take a section here and you say moment at C equals, and assume yourself also you are sitting just like this here, and if the moment is going up, it is positive, and if it is going down, it will be negative. So I will stop here and I will say summation of M, or just M at C equals, okay. Then you will look here, just put your hand here and cover this part, and then just concentrate only on this right side or bottom side, and you will see that the moment at C equals 24 going down, so it is negative, times 4, 24 times 4 in negative, so it will be minus 24 times 4. How much it will give us this one? It will be 96, and it will be like a negative moment. So the moment here will be like a negative moment like that with a value of 96. Where to draw this moment? I draw the moment always at the tension side, so at the tail side. So I will always draw the moment at the tail side, and as I explained in my previous videos, we draw the negative moment up and the positive moment down. So when we have a frame, outside will be the up, this is here will be negative moments, and inside will be just the positive moments. So you have here 96, it is a negative moment, okay, compared to you here, it is going down, so it is negative moment, and the tail side is out, so this 96 will be here, and it will be minus 96. Add the same connection here at this point C. The moment here should be similar to the moment here. If it's outside, it will be also outside, okay? Assume that there is a circle, and this is the center line of the circle. So if you have 96 here, it will be the same 96 here. So just directly I can take this value, and I assume this is also 96, and it is a negative moment as well. So now we found all the moments at this connection or these points. We need now to connect these points together. Let's do that. Okay, how to connect them? Let's start from point B to C. I don't have any load, no load, so it will be a straight line. So what I will do, I will make a straight line like that from here to here, and this will be the first part. And as I told you, outside will be just a negative moment. How about from D to C? We have a uniform load. So for uniform load, the moment should be a curve, should be a parabola. How to do that? Just you can make a dot line like that, and assume that there is this point and that point, we are connecting them by an elastic. And if the load is pushing down like that, so this will take this elastic down as a curve. How it will be? It will be something like that, and this will be our curve. You know that the value that we have it here, okay, from this point to this point is the WL square over 8, which is the famous case of bending moment under uniform load. You know, this is a famous case when you have a beam like that with a span L and a uniform load W. This is one of the basic cases that you need to know. The moment will be just a positive moment, and the value is WL square over 8 at the middle. So at the middle here, we can get this value by subtracting WL square over 8 from the values that we have it here, which is not useful in this case because the maximum will be somewhere shifted to this point here, and we'll see together how to get this maximum. So the moment here for that part, we know it is like that, and we draw it minus 96, and we go down like that. So this part will be just a negative moment, and this part will be a positive moment. We need to know M max, which is at the zero shear. Okay, let's keep this until the end, and then we finish with the last member, which is the member AD. Member AD, it starts by 0 and ends by 0, and you have a uniform load pushing like that. So again, assume that there is an elastic here and the load is pushing like that. So how it will be the moment? The moment will be like that, which is this case, WL square over 8. So this is a straightforward. The moment will be like this, and the maximum values that we have it here, which is WL square over 8. Here, the W is 8 kilonewton, which is this 1 kilonewton per meter. L is 6. So just we said 8 times 6 square over 8. So 8 will go with 8. It will be 36. So the maximum moment that we have it here is 36 kilonewton meter. And it is inside. It will be like a positive moment. So we finish the moment, the only missing one, which is the M max. How to get this M max? We can get it back from the shear by knowing this area and getting this X and getting the area from shear. But if you don't have the shear and you need to get this value, so we have to assume a distance here called X, where the shear equals 0 at this point, and you make a small equation. To get this X, it equals the reactions that you have it here divided by the uniform load that we have it here. So it will be 30.8 divided by 20 equals how much? Let's calculate this together. So 30.8 divided by 20 equals 1.54 meter. This is 1.54 meters. Okay, so let's get the resultant of this part. The resultant of this part here will be 20 times X. 20X. So 20 times X multiply 1.54 times 20. So this will be 30.8 kilonewton. And the distance that we have it here is half of the distance, 1.54. 1.54 divided by 2 equals 0.77. Now, how to calculate the moment at this point here? We take a section and we get the moment here from this part. Okay, how to do that? Okay, let's get an equation for that and we calculate the moment here. Because I have an intermediate hinge here, so I know that the force here is 30.8. If I cut this part, the force here is 30.8, and the horizontal force here is 24, which is the equals to 48 minus 24. So I don't need this part because I already took the components here. So we can take a moment here for this part. So how it will be the moment? I will say M at this distance X equals how much from left side? 30.8, which is this value here, multiplied by X, which is 1.45, minus 30.8 as well, times X over 2, which is 1.54 divided by 2. This will give us a value of, let's see it together. So it is 30.8 times 1.54 divided by 2 equals 23.716 kilonewton meter, and this will be the maximum moment, 23.716, and it is at a distance equals to X 1.54. This concludes our video, today's video. If you like the video, please like and subscribe to encourage me to make more videos. Thank you for watching and looking forward to see you again in a coming video, and goodbye.